Hey everyone, and welcome to another deep dive. Today we're going beyond the realm of everyday physics into a world where particles dance as waves and empty space hums with energy.
Sounds exciting.
It is, and we're going to explore all of that and more as we delve into Waves in an Impossible Sea by Matt Strassler.
Oh, that's a great choice.
It is. This book promises to reshape our understanding of the very fabric of the universe, and I can't wait to unpack it with you.
I'm ready when you are.
Okay, so before we get swept away by these cosmic waves, let's first set the stage. Who is Matt Strassler, and what led him to write this mind-bending book?
Well, Strassler's journey began with, just a childhood fascination with science.
Yeah, I could see him like tinkering in his, parents' basement.
Exactly. Always questioning how things worked.
Yeah.
That led him to Harvard and Stanford, where he really honed his skills as a physicist.
Okay, so he obviously enjoyed the academic life.
He did, and it ultimately culminated in a professorship at Rutgers University.
Wow, impressive.
Yeah, and on top of that, he also did research at some of the world's leading institutions.
So definitely a strong academic background.
Absolutely.
But it sounds like his passion extends beyond just the traditional academic world.
Totally.
Like what sets him apart?
Yeah, his dedication to making complex physics accessible to everyone. Like everyone.
That's fantastic.
Yeah, his website and blog are testaments to that commitment. He breaks down intricate concepts with remarkable clarity and just engaging prose.
Nice, I like that.
Yeah, and Waves in an Impossible Sea is like a culmination of this passion.
Oh, cool.
You could call it his magnum opus to illuminate the often misunderstood world of particle physics.
Now, the title itself, I have to say, is a masterpiece.
Right, agree.
Waves in an Impossible Sea is so poetic.
It is.
Almost mystical.
It sparks immediate intrigue, and it's a brilliant encapsulation of Strassler's central thesis.
Oh, interesting. So how does it connect to his main argument?
Well, he challenges this common perception of particles as tiny, solid objects.
Right, okay.
And instead reveals them to be ripples in a sea of quantum fields.
Okay, hold on, ripples.
Yeah.
In a sea.
Yeah, but the sea, of course, is not made of water or any substance we can, directly perceive. It's a realm of pure energy and potential, a realm where the very laws of physics seem to bend and twist.
Okay, this is where it starts to get really interesting. So Strassler is setting out to kind of replace our simplified, I guess, cartoonish view of particles with a much more nuanced and, mind-blowing perspective, right?
Right. And one of his primary motivations for writing this book was to dispel those misleading narratives that surround physics.
Okay.
Like particularly the hype surrounding the Higgs boson as the God particle.
Oh, yeah. Remember that.
He felt it was crucial to provide a more accurate and deeper understanding of particle physics.
Okay, I'm starting to understand his mission here. It sounds like he's not afraid to challenge conventional wisdom and invite us to think differently about the universe and our place in it.
Exactly.
So what were some of the key ideas that emerged from this mission?
Well, he starts by dismantling some of our most basic assumptions about the physical world, beginning with motion.
Okay.
He argues that our intuition about motion is profoundly shaped by friction, a force that's ever present in our daily lives.
Yeah, like a ball will eventually stop rolling.
Exactly.
Cool.
Because of friction. But Strassler invites us to imagine a world without friction.
Okay.
Where objects in motion would continue moving forever in a straight line, never slowing down or changing direction.
Oh, interesting.
And this, he explains, is the essence of Galileo's principle of relativity. Steady motion is undetectable.
Okay, so our perception of motion is really just tied to our experience on this friction-filled planet.
Exactly.
Makes you wonder, what other biases might be shaping our view of reality, right?
That's a great point. And Strassler doesn't stop there. He challenges another common misconception, the conflation of mass and weight.
Oh, okay. Interesting.
He uses this humorous anecdote about a student who joked about going to the moon to lose weight to illustrate this point.
Okay, I'm all ears. I love a good science joke. What's the joke?
So Strassler recounts how another student pointed out that it's not weight you want to lose, but mass.
Oh, right.
And it's a lighthearted way to highlight the fundamental difference between these two concepts. Mass, he explains, is an intrinsic property of an object, a measure of its resistance to changes in motion.
Okay.
Weight, on the other hand, is the force of gravity acting on that mass.
So even though your weight would decrease on the moon due to weaker gravity, your mass would remain the same.
Precisely.
It's a subtle distinction, but it's crucial for understanding, like, the nature of matter.
Absolutely. And Strassler brilliantly uses these seemingly simple concepts, motion, mass, weight, as a springboard to launch into far more profound and mind-bending territory.
Okay, I'm intrigued.
He seamlessly connects these ideas to Newton's laws of motion and Einstein's theory of relativity, demonstrating the interconnectedness of classical and modern physics.
This is where it gets really exciting.
Mm-hmm.
The transition from the familiar world of everyday physics into the realm of waves, fields, and quantum weirdness.
Exactly.
I think we should probably pause here, take a breath, and dive into that fascinating territory in part 2.
Picking up where we left off, Strassler guides us from that kind of familiar world of classical physics into the uncharted depths of waves and fields.
Okay, I'm ready to take the plunge. But when I think of waves, I'm thinking like crashing ocean waves, ripples in a pond. How does that relate to like the fundamental building blocks of the universe?
Right, that's a natural starting point. And Strassler acknowledges those familiar waves, but he wants us to expand our thinking.
Okay.
He says everything in the universe, from the smallest particles to the largest stars, is made of waves, but not the kind we can see or hear.
Oh.
These are waves that are propagating through quantum fields, which permeate all of space.
Interesting. So these fields are like the medium through which these waves travel.
Exactly.
Kind of like how sound waves travel through air.
Yeah, that's a good analogy. Just as air is the medium for sound waves, these quantum fields are the media for the waves that make up particles.
Okay, but these fields are like fundamentally different from anything we encounter in our everyday experience, right?
Yeah, they are.
So what makes them so unique?
Well, unlike substances like air or water, which are made of molecules, these fields are more like properties of space itself. They're transparent, permeable, and they don't exert any drag on objects moving through them.
Interesting.
Strassler even coins the term emotional to describe them, because our motion relative to these fields seems to have like no meaning.
I love that it's like they're there, but not in a way we can easily grasp, almost as if they exist in like a different dimension of reality.
Exactly, and this leads to a really mind-bending concept.
Okay.
This idea that empty space, the vacuum itself, might be a kind of medium. It's a medium that's vastly different from anything we're used to, but it possesses properties that allow waves to propagate through it.
Okay, my brain is definitely starting to bend. So we've got these fields, which are like the fabric of reality, and waves are traveling through them.
Right.
But how do particles fit into all of this? Like, where do they come in?
That's where things get really interesting, where we enter the quantum realm.
Okay.
Strassler explains that in the quantum world, energy can't just take on any value. It's quantized, meaning it exists in these discrete packets, almost like tiny bundles of energy.
Okay.
And these packets of energy are what we perceive as particles.
So instead of picturing particles as tiny billiard balls, we should imagine them as these concentrated bundles of energy vibrating within these fields.
You're getting it, but there's an even deeper layer to this.
Okay.
These bundles of energy don't just sit there, they also behave like waves.
Oh, wow.
Strassler captures this dual nature by calling them wavicles.
Wavicles. Now, that's a word that really captures the essence of quantum weirdness.
It does.
It seems almost paradoxical, particles acting like waves. How can something be both a localized particle and a spread-out wave at the same time?
It's one of the great mysteries of quantum mechanics, and it defies our everyday intuition.
For sure.
But countless experiments have confirmed that this is how reality operates at the subatomic level.
Wow.
And this dual nature of wavicles leads to some truly mind-blowing phenomena, like the famous double slit experiment, which demonstrates that wave-like nature of particles.
Right. It's like those particles somehow know whether they're being observed or not, and they change their behavior accordingly. It's enough to make you question the very nature of reality.
It certainly challenges our assumptions about the nature of objectivity and observation.
Yeah.
But getting back to Strassler's book,
Okay.
he explains how each type of field has its own corresponding wavicle. So the electron field has electrons, the electromagnetic field has photons, and so on.
So all these particles we've learned about, electrons, quarks, photons, they're really just different types of wavicles. Each vibrating within its own specific field. It's like a cosmic orchestra, with each field playing its own unique tune.
That's a wonderful analogy, and just like an orchestra needs a conductor to harmonize all the different instruments.
Yeah.
The universe needs something to orchestrate the interactions between all these different fields and particles.
Okay.
And this is where the Higgs field enters the stage.
Ah, the Higgs field. The source of so much mystery and fascination. I've heard it described as the God particle, but it sounds like Strassler takes issue with that oversimplification.
He does. He carefully deconstructs that misleading moniker, explaining that the Higgs field, while crucial, is not the ultimate source of all mass or the creator of the universe.
So what exactly is the Higgs field, and what role does it play in this grand cosmic orchestra?
The Higgs field is just that field like the others we've discussed, but it has a unique property. It interacts with other fields, imparting a kind of resistance to them, a stiffness, if you will.
Stiffness. Can you elaborate on that? It's a bit hard to picture a field being stiff.
Right. Strassler provides a helpful analogy, a pendulum. Think about how a pendulum swings back and forth at a specific frequency, which is determined by the stiffness of the pendulum's rod and the strength of gravity.
So the Higgs field is like a cosmic gravity influencing the vibrational frequencies of other fields.
It's similar in that it affects the frequencies, but it's not gravity itself. The Higgs field is a distinct field with its own unique properties. The key point is that this stiffness imparted by the Higgs field influences the resonant frequencies of other fields. And this, in turn, determines the rest mass of their wavicles.
So a particle's mass is essentially a measure of how strongly its corresponding field interacts with the Higgs field.
Precisely. And this leads to another fascinating concept, the vacuum energy of fields.
Vacuum energy. Now, that sounds like something straight out of science fiction.
It might sound like it, but it's a very real and fundamental concept in quantum field theory. Imagine a guitar string that's not being plucked. Even when it appears to be at rest, it still has a tiny bit of vibration.
So even in a state of apparent emptiness, there's still a subtle energy present.
You got it. And this vacuum energy is not just a theoretical curiosity. It has real, measurable effects on the universe.
This is where my brain truly starts to melt. So the Higgs field interacts with other fields, giving them stiffness, which affects their frequencies and the mass of their particle. And on top of that, there's this vacuum energy that's also at play. Influencing the Higgs field itself.
Exactly.
It's a lot to take in.
It is. And this intricate dance between the Higgs field and the vacuum energy of other fields leads to some profound puzzles, like the hierarchy problem.
The hierarchy problem, that sounds ominous. Perhaps we should save that for part 3, along with the implications of all these mind-bending concepts.
Indeed, the hierarchy problem takes us even deeper into the mysteries of the universe and the search for a more complete understanding of reality.
Welcome back to our deep dive into waves in an impossible sea. We've been on quite a journey.
We have.
From the familiar world of, everyday objects to the ethereal realm of quantum fields where particles dance as waves and empty space just hums with energy.
It's pretty amazing stuff.
It is. But as we ventured deeper, we encountered a perplexing puzzle, the hierarchy problem.
Right. And the hierarchy problem emerges from that intricate interplay between the Higgs field and the vacuum energy of other fields. The math, based on our current understanding, suggests the Higgs boson should be astronomically heavier than what we observe.
So the theoretical predictions and the experimental observations are dramatically out of sync.
They are. To grasp the scale of this discrepancy, imagine comparing the weight of a grain of sand to the weight of Mount Everest.
That's a huge difference.
It is. That's essentially the difference between the predicted mass of the Higgs boson and its actual measured mass.
Wow. That's an enormous gulf.
Yeah.
Does this mean like our entire understanding of particle physics, the standard model, is flawed?
Not necessarily. The standard model has been incredibly successful. Accurately predicting countless phenomena and withstanding rigorous experimental testing. However, the hierarchy problem suggests that it's not the whole story.
Okay, so it's incomplete.
It hints at something more, something beyond the standard model that we haven't yet discovered.
So it's like we're missing a crucial piece of the puzzle.
We are.
A piece that could revolutionize our understanding of the universe. What are some of the ideas that physicists are exploring to solve this hierarchy problem?
Well, there are many fascinating avenues of research. One intriguing possibility involves supersymmetry.
Okay, I've heard of this.
This theory proposes that for every known particle, there exists a supersymmetric partner particle with slightly different properties.
So it's like a mirror universe of particles.
In essence, yes.
Each with a hidden twin.
And these hypothetical supersymmetric particles would interact with the Higgs field in a way that could counterbalance the contributions from known particles, effectively stabilizing the Higgs boson's mass.
Okay, so that's a pretty elegant solution. But haven't we been searching for these supersymmetric particles for decades with no luck?
We have. So far, experiments haven't yielded any direct evidence for their existence. But the search continues, as do explorations into other potential solutions to the hierarchy problem.
So what are some other ideas that physicists are considering?
Another compelling possibility lies in the realm of extra dimensions.
Extra dimensions, you mean beyond the three spatial dimensions we experience?
I do.
Like something out of science fiction.
It might sound fantastical, but some theoretical frameworks suggest that there could be additional spatial dimensions curled up at incredibly small scales, too small for us to perceive directly.
So these extra dimensions would be like hidden pockets of reality.
Yeah.
Influencing the behavior of particles and forces in ways we're only beginning to understand.
Exactly. These extra dimensions, if they exist, could profoundly impact the interactions of particles with the Higgs field, potentially offering a solution to the hierarchy problem.
It's incredible to think that our familiar three-dimensional world might be just a tiny slice of a much grander multi-dimensional reality.
It is a truly mind-expanding concept, and it speaks to the power of Strassler's book. He doesn't shy away from these profound questions. He uses them to illuminate the frontiers of knowledge, to spark curiosity, and to encourage us to think deeply about the nature of reality.
He's definitely done that. For me, this exploration of fields, wavicles, and the hierarchy problem has completely reshaped my understanding of the universe. But beyond these grand cosmological questions, does Strassler offer any insights into the implications of his ideas for us, for life itself?
He does. In a beautifully poetic passage, Strassler reminds us that the energy we carry within us, the energy that gives us mass, is a remnant of the Big Bang.
Wow.
It's a cosmic echo, a memory of the universe's fiery birth woven into the very fabric of our being.
Wow, that's a profound thought. So all the matter that makes up our bodies, the planets, the stars, it all originated from that initial burst of energy.
That's the current scientific understanding, and it highlights a crucial difference between macroscopic objects and elementary particles.
Okay.
Every raindrop, every grain of sand is unique.
Yeah.
With its own distinct mass, but all electrons, all protons are identical.
They're like perfectly matched notes in that grand cosmic orchestra.
Exactly. Their identical nature arises because they're all wavicles of the same fundamental field.
Okay.
And this leads to another remarkable principle, the Pauli exclusion principle. Remember how we talked about fermions?
Yes.
Well, this principle dictates that two identical fermions can't occupy the same quantum state.
I recall that concept. It's a seemingly simple rule, but it sounds like it has enormous implications.
It does. The Pauli exclusion principle is what prevents atoms from collapsing in on themselves.
Oh, wow.
It's what gives matter its solidity, its structure, and it's also what leads to the incredible diversity of chemical elements, the building blocks of all the complexity we see in the universe.
It's mind-boggling how such a fundamental principle operating at the subatomic level can have such profound consequences for the emergence of stars, planets, and even life itself.
It's a testament to the interconnectedness of everything from the tiniest wavicles to the largest cosmic structures. It's all governed by these fundamental principles. And Strassler masterfully reveals these connections, weaving them into a captivating narrative that illuminates the hidden beauty and order of the universe.
Yeah, he takes us on a journey of discovery from the familiar to the utterly mind-bending, and leaves us with a sense of awe and wonder about the universe we inhabit.
And in that spirit of wonder, Strassler concludes his book with a thought-provoking question.
Okay.
He asks us to imagine a world where life isn't based on atoms, but on wavicles.
Okay.
On the fundamental vibrations of the universe's fields.
I like that.
What would such life be like? How would it perceive reality?
It's a question that sparks the imagination. It's a reminder that the universe is full of possibilities, full of potential that we're only just beginning to explore.
It is. Waves in an Impossible Sea is a brilliant guide for that exploration, a book that encourages us to question our assumptions, to embrace the unknown, and to marvel at the intricate beauty of the quantum world.
Well said. This deep dive has been an incredible journey into the heart of matter, leaving me with a profound sense of wonder and a thirst for further exploration. Thank you, Matt Strassler, for sharing your insights and passion with the world. And to you, our listeners, thank you for joining us on this adventure. Keep questioning, keep exploring, and keep embracing the mysteries of the universe. Until next time.